What is up, my friends, and welcome to Bear Science, where I describe sciencey things in the way that I think about them, because I think that it is a unique take on sometimes obscure or strange subjects, but also very relevant. Um, so today I'm excited to be talking about enzymes. Enzymes, catalysts, catalytic action, proteins inside the body that do the things that you need to get done. So enzymes are amazing because if you look at what a body needs to do, or a cell or an organism needs to do to keep things going along, they need to take in raw materials, change those raw materials into something else and energy, and that something else could be like part of their body, or it could be like a little signal I need to send out, or it could be like a product I need to generate for the greater organism. Those are all things that they can be doing. But you need something that makes that happen. Like, there's no such thing as a free lunch. Thermodynamics tells you that. So there's like energy you got to put in to get things done, but you want to make it easy. You want to make it happen fast at low temperatures, because who wants to work hard and get nowhere when instead you could have this magic thing that makes your shit go fast and work? Tech, is technology. And so how do we do that? And to answer that question, we have to talk about a couple things. One of the things is, what are our building blocks, our raw material that I was saying is the thing that we start with that we want to change into something else useful. And what's that thing useful? It turns out, well, that's one question. And then the other question is, okay, I know what I start with, I know what I end with, but how do I make it get from there to there? It wants to get there. How do I get it there? How? I don't know. Let's find out. I do know. Let's find out. I do know. Or so science tells me. I am trusting a bunch of things. Anyway, the things I start with are proteins, raw proteins, or amino acids, or whatever. Depends on what you're trying to do. It's usually a protein, though. And the thing that you're ending up with is a protein. So what is a protein? A good way to think of a protein, or a way to think of a protein, is imagine a big, long metal chain, like links. And imagine just kind of how something of that shape moves. Like, it can curl and twirl and just kind of like flop around. That's sort of what it does. Now imagine like a bunch of those, and there's like, I don't know, 1,000 links, or like long things. It's a sea of golf balls. And if you think about it, the golf balls can kind of surround the chains. There's more golf balls than there are chains. And if you were to stir that mixture, it's just kind of like everybody's doing this. They're all surrounded by things. It's just what they're doing. It's fine. This metaphor, the chains are proteins. They are long repeat units of stuff that's linked together. And the golf balls are like water, or whatever you happen to be in. But in biology, it's typically water. That's why you have to drink 8.5 glasses of that nonsense all the time, etc. So, we're going to take that chain and we're going to make it fancier. So imagine this chain, every link I have on it has like a different doodad hanging off. And the doodad that hangs off of it could be like bleh. Different shapes. It could be like a long bleh, or like bleh, bleh, bleh. Those are all different things that it could be. And different parts of the bleh might be sticky of sorts. They can either like generally want to stick to stuff, or maybe specifically want to stick to a couple things. And if you imagine you have a long chain where parts that are sticky to each other, you get situations where it's like, oh, I'm sticky over here and I'm sticky over here. Yeah. If you do that enough and like plan out your spacings just right, you can get basically whatever weird ass shape you want to get. You can have a large coil, like I was talking about a chain. Imagine the chains, you were probably like thinking 100 links, like, oh, that's pretty long. Like, try like 3,000, 300,000. If you have a chain with 300,000 links, that is like a big gobbledygookedy mess. On average, it's closer to itself more than it's close to the things around it because it's always attached to itself. And as a result, favorable sticky interactions with itself are more favored than sticky interactions with the stuff that's surrounding it. Which means that if there is a very stable configuration of that chain where any opportunity it has to bond favorably to itself somewhere happens, like all those things that are likely to happen do happen, if that thing gives you a shape that you want to have, then that thing will happen a lot and you have that shape a lot, so it just like always kind of hangs out there. And sometimes like afterwards you can just like glue it together and be like, okay, well you're pretty much here most of the time, stay there, like welding, whatever. That's a thing, but I don't care about that right now. So we're talking about those long chains that we're trying to start with and then change into something else. And I told you can get whatever shape you want with anything. And so the kind of entire principle behind it is if there's a change that you want to have happen at a specific place, the enzyme, which is the thing I got all excited about at the beginning. I went on a long tangent trying to describe you the players here. The enzyme is basically a giant globby ball of basically a shape that has a little inset in it that has a space for the important part of the thing that the enzyme's working on to nest right into. And so when it nests there, oftentimes the changes that you're trying to do are really slight, like you're either trying to break something apart, join two things together, in which case you have both of them kind of come close, and or like have stuff that's already there, just like rearrange a shape, like switch. And basically I was talking about envisioning it as a chain, like a big sequential chainy kind of thing, metal chain. Instead of thinking the chain is each link is a link, instead think a chain is like 4 billiard balls or 3 or 4 billiard balls that you're trying to hold in space. And you're just like bleh, 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 bleh. And put those next to each other. And kind of imagine just like mashing it up, mixing them in a certain way. You can envision that if you had a racetrack of sorts that gave individual balls a path to get where they need to be through simple switches or following simple rules, you can kind of imagine that that same thing could happen with atoms changing and rearranging shape because you give them the right racetrack to jiggle through and get to a predetermined final position. And that's basically all there is. Like, it was a whole bunch of kind of saying, hey, this is what this thing looks like, and this is what this thing looks like. But once you have the players in place and you understand what needs to happen, which is typically a simple change, the mechanism of having it happen, yes, it's obscure to find the specific solution, but the general solution, the thing that you're trying to do, becomes pretty obvious. And so once you accept that, it gets easier to accept the idea that, hey, if I roll a bajillion dice all asking, get me the highest number you can, eventually one of those die is going to do that, and it remembers it, and that's evolution. I don't know, words, big jumps, but I got excited. A little excited.